Yo, I'm Łukasz. 2 years ago, I couldn't write a single line of code. Now I work as an AI engineer. Today, we are looking into building a transcription-ready production server in vLLM. This will allow us to asynchronously transcribe multiple audio files into the text, so it's perfectly suitable for your AI projects. Now, let's start by building the environment that we'll use. So as we can see, we will start by doing item 3M. We create a virtual environment, name it Path. You can see it's getting created. Now we do source.path bin activate. Yes, now we activated the environment. We can do pip install upgrade pip. Mistake, but we'll deal with it. So we updated pip, and now we just install OpenAI to test our code. Yes. And now what we need to do is to build a file. So I have this file that I built. And if you watched the first episode about text, we need to do some things a bit differently. So vLLM have dedicated package to manage audio, like generating audio and transcribing audio. So we need to build this image to make it simple for you guys. I use special Docker compose command. So we'll be building this from Docker file. We'll name it STT. We'll run it using NVIDIA. We need Hugging Face token. This is example how you can create an variable to save it. I will change the ports. So I will run it on port 8002, not 8000, like it's typically done. We connect IPC to host. Then we will mount the volume to our default cage for Hugging Face models and design the dedicated GPU memory utilization, define the task. This I will comment because we want to show things first. So Docker compose build. As you can see, it was caged, so it was fast. Now we can do Docker compose up and run it in the attached mode. You can see the container is starting. And now let's look into the logs. This is Docker plugin from VS Code extensions that I'm using. So now it will run. You can see max model length 448, which will be important later. We are loading the checkpoint shards. We can see how much model loading took. It was quite fast because I already ran it before, and as we can see, I'm out of memory. This means that I'm pretty much poor. Why I'm poor? Because if we go into NVIDIA SMI, we can see that I have GeForce RTX 3060 laptop versions, only 6 GB of VRAM. So this could happen to any of us. So now my trick is to use this because this will reduce the number of concurrent requests in a batch and effectively the number of CUDA graphs we compute and how much space we require for the KV cage. So now all I need to do is do Docker compose up again. We can go into logs and this will run just fine now. Yeah, so this will be running. I'll prepare this. So as we can see, again, GPU memory utilizations. Here we now see that maximum number of sequences is 2. We can see that before it was not specified, so it goes to default value. So now we see maximum concurrency per request is 10.404. We can note it down in our compose. That could be interesting for us later. And now the server is running. So if I go here, if you watch the first video, you know it will not run because we changed the port. So it will run on 8002 and I added docs. And here we have all instructions that we can use and check our server. But to make it simpler, I wrote this code that will basically make this call of us. And I created audio file using AI because that's what we do. And I can specify the number of requests also to check how it works. You can see very good job by the AI, as always. At least they will not replace us so quickly in this case. Now, what will be the interesting thing to see is to run it. So I will run it now in the code. Created another terminal. So we can clean things up a bit. And as we can see, this takes a very long time. Why it happens? So yeah, it was in first episode about text 2. So vLLM never warm up their models automatically when you start it. So if you run it now again, you will see that it will be faster, much faster. So this happens because it needs to warm up the model, so means compute everything and prepare for us to run inferences. Typically, it's done automatically in Ollama CCP, but here it's production ready, so you do it yourself. Here, as we can see average tokens and so on. Now let's, for example, we can send the same input twice at the same time, and let's see what happens. As we can see, the resources change a bit. I mean the times, because it was 500. Now we have the average of 699 because we needed to reduce the MR bit the sequences, so it's getting a bit slower. But if we would do it concurrently, it will take over 1 second to get the next one. So here is how we save time. Now, for example, I can do 10. Let's see what happens. We can go to the server. We see we get all these responses. We should see the response soon. They go into the queue like before. We have 2 requests. Now we can see we have 54 tokens per second. And here we have all our results. So as we can see, they get a bit mixed up because the scheduler define how they are going, but we have the average time of 2 seconds. But this is because we really reduce the graphs that are needed to do concurrency just for the sake of resources in this video. So now let's jump into another test because here we just have the same file, which is kind of boring. The cage gets it each time and so on. So here we could, for example, see, I will change it to MP3 for now. Here we can run it and we will transcribe 10 different files in this format. The interesting part is that one file is super big. It's 2 times bigger than average of these files. They have like 20, actually 3 times bigger. Yeah, depending on the file. Maybe to say what is this. This is a plugin that allows you to see information about audio quickly in VS Code, which is very useful for me. If you want to check this plugin, it's here. It's audio preview. And before, I use Docker to manage my Docker containers, which give me this window that I can quickly interact with my containers, images, registries, and so on. Now, as we can see, we have many different outputs. And the average time is 2 seconds, and the longest time is 3.8 seconds. So now what we can do, we can rebuild this image. Let's reduce the max model length. The default one, if we run it here, it's at the top. As we can see, it's 448. Let's do 100. I will use this to quickly build it up. You can see it builds. This should be replaced. Yeah. Now we go into logs again, and we'll do this test. So because I need to warm up model, I will use this to quickly warm warm it up with one request. So we can see max model length 100, GPU memory utilization, max number of sequence. We go. And the information I want to show you guys is the concurrency that we noted before. So before we have 10.04, and now the concurrency is 44.96. So it increased nearly 4.5 times. And now let's do one quick request to warm it up. It's running. Let it warm up. We'll do again 10 different requests at the same time. It should be, yeah, ready. We can see now it will provide also these messages. Yeah, so now with this line of code that will transcribe all our MP3 files, we can see we start getting responses, and boom, we get them again. We have now the average 2, the longest 3.7. And if we can see it here, we have 258, 378. So it gets faster a bit, yeah? And now the important also part that I want to show is I will copy this one. This is the longest one. As we can see, the 60 seconds of audio. I will put it in the text compare for later. And now let's, for example, we can compare this one together. Let's see what happens. Okay, other than space from my bad copy pasting, looks the same. So this change basically allows us to have higher concurrency parameter. And now why it happened? So at the beginning, we ran a 448 max model length. This defines also the number of tokens. And vLLM computes how much of memory we should have ready for the CUDA graphs, KV cache, and for the attention. And attention scales quadratically. So even if we have, for example, small input, if we reserve this much memory, it's blocked. So that's why the maximum concurrency jumps so high, because we reduce the maximum model length and we get higher concurrency. Yeah? So now let's say, so now we could say that, okay, so we should always lower it. Like if I 100, give me a bit speed boost and I can manage much more requests at the same time. Then what will happen if we do 50? So now let's rebuild it again. And let's see how much we'll get. We need to again run one warm-up. When it starts. So yeah, we can see now we have maximum model length 50. And now maximum concurrency requests is basically doubled than the last one. So 89, 92. Let's copy paste it here. So this is 448. This is 100. This is 50. Yeah, exactly, Copilot, my old friend. So now we warm it up quickly. And we'll prepare this. We can see when it will compute and warm up itself. So what I want to show you is how you should optimize it actually and what you should look for. So now it's warm up, and now let's run it again. So we have 2 seconds. In the last one 100, we have 245 and 3 seconds 700 80. And now, as you can see, it's much lower. Average time 1.7. So we save around 300 milliseconds. And longest time it's 3.7. And here it's 3.12. So now you could say, oh, that's better. That's much better. We should use it. But there is caveat to it. If we look into our output, for example, so let's look at this output and do misclick. Of course, let's do quick search. So this is from 50 and this is from 100. So as you can see, we lose some information because we define number of tokens, and when we go over this number of tokens, it stops and we don't go further. So if you do application like this, you basically will be cutting out the last part of audio that was sent. And that's also why I copied the text before, because I wanted to show you something interesting. So like, if we do it, you would expect that like if I compare beginning and end of the sentence and they are the same, then it means that we have full text. But actually, in this case, we cut out things in the middle and here. So we get actually the last part of sequence sentence. So if we could compare it, I got and nightmare, and we here got also I got and nightmare, but it deleted the middle parts. So this could be quite hard to catch for you. Now, what I also want to see is to change of the files. The only thing I should do, I make quick script to change the files. As we can see, MP3 was in 44,100 sample rate. So let's do it the same here. Typically it was 16,000. We'll get into it at the end of the video. So now, yeah, wave. Let's do it. Quickly change it. Now we can see our wave files are in the same format. And let's run. So before, that's pretty long scroll. Okay, I don't. We got 1.7, 3.2. Now we got 1.7, 3.2 with a bit of difference. So you would say, we don't care about which file we use, but actually there is difference because WAV file don't corrupt audio and MP3 corrupt audio because it's compressed. So I make small table that we can walk through, actually not table. So the frequency rate, as I said before, we typically use 16 KY because it's sufficient for speech transcription as it covers the core frequency range of human voice. If you will transcribe animals or something else, then you need to go into frequency range of the sound they produce. And as we can see, we have many options of audio. For example, this model manage WAV and MP3, that's why we use it. But for example, WAV is uncompressed, so it preserves all audio details and results in highest transcription quality, but with largest file size. The file size here could be a problem because if you transfer it over network, you need to transfer more data, which give you more delay. Now, there is also FLAC, which I heard is quite commonly used because it's lossless compression, but it's lower size than the wave. So you maintain kind of optimum between the size and losing information from audio. And then MP3 discards some audio data to reduce the sizes, and it lowers the transcription accuracy. Then we have also channels. So typically you could use just one mono channel because as before, two mono channels are not providing as much information and make the file a bit bigger. And this could maybe affect accuracy and the model compatibility. Most models work in one channel. Yeah. So that's what I wanted to show you. And for example, the max tokens, we could send some files and see at how many seconds we, for example, get the cut of the audio and adjust it, or we could provide the recording, for example, we can cap the recording on our, let's say, front-end application. We can also just split the audio and send 2 requests and then connect it together. If we do it asynchronously, then it's also nice, yeah, because we could compute 2 parts at the same time and then connect them together and give to the user, which will make it like twice as fast, as we can see. We don't see also as many gains in this case because my GPU is pretty bad. And what I wanted to for example, show you, we can see that Whisper has a receptive field of 30 seconds. And here you have, for example, advices. So you should always check the model you use and the model card. And let's say, yeah, we have also README, supported languages, license, which is quite important if you do anything for a company, to not get them sued, and so on. So now I will come on to my last topic because, for example, English is quite easy task, and model which we use, which is Whisper 3 Turbo, works quite well, yeah, and it is we can scale it, which is pretty nice. But let's say you work in languages that are harder, like let's say, for example, Dutch, which have pretty low accuracy scores and so on, because there is not much data in this language. So this, if you use this model, you will have a bit of trouble because it will not transcribe everything perfectly as we want to. So there are like other solutions, because Whisper is very popular model and it have many different ones. I think in README I provided this information. Yeah. So this is the base open source model, like Whisper base, small, medium, large turbo, and large. The turbo is basically reduce the size a bit with the cost of accuracy, but increase the latency. But we have also other solutions, like if we go to faster Whisper, for example, this is a solution that is quite fast and it takes much less memory, but it don't scale itself, at least according to what I know up to today. But they provide, for example, many implementations that make the audio recognition and transcription easier, like filters and so on. We have like also Whisper X and so on. So it's good to check multiple models and what they do. Like here we can see we have, for example, voice activity detection. So you can cut the silences, connect the audio, then you make the job of the transcription much easier. So there is many things you can do to speed it up and make it better. And each implementations have different or similar of them. So you need to adjust them yourself, basically. Okay, so that was this for today. If you like this video, like and subscribe. In the next episode, I will try to go into text-to-speech and also try to scale it. We'll see if I can manage it on these resources. If not, I will think of something else. So yeah, see you guys next time. Bye.